I decided to record a video to talk about this problem. It's a very interesting problem. Number of sequences that satisfy the given some condition. So I will save you from details. The problem says that you have a list of numbers like this one, nums, and a target number, and you would like to find all the subsequences that satisfies the condition that summing the minimal number with the maximum number from that subsequences will produce a result less than or equal to target. So if we look for this example here, you're going to see that these are all the value subsequences that summing the minimal with the maximal will produce a value less than 9, which is our target. So the first subsequence is a subsequence is 3, because 3 plus 3 is 6 and is less than or equal to 9. And we keep doing this, and you I'm going to realize that we only have 4 subsequences that satisfies this condition. Yeah, so to solve this problem, you're going to need to understand a little bit about combinatory analysis and also probably binary search and probably backtracking, because this would help you in your thought process. So my thought process to solve this problem was this. So initially, I tried to solve it in the most dumb and brute force way, like the naive approach that any human being would have. So I tried to maybe use some sort of backtracking or um, memoization with a dynamic programming would solve this, because I realized that um, it's a problem of, let's say here, for instance, um, I would pick 3. So once I pick 3, I will need to pick other numbers here. So imagine that I try to pick 5. Then in other choice, I will not pick 5. I will skip 5 and pick 6, for instance. So this would be like a decision tree of pick and not pick. So you would have something like this, like imagine here, so this would be pick 3, and this would be, let's say, pick nothing, for instance. So once you pick 3, now you do a decision here to pick 5 or keep only the 3 here. And you would do this, so here you would pick 6, so 6. So you would have a huge decision tree, and whenever you see that the sum of the maximum and the minimum from this decision tree is less than or the target, you would increment the result. So you would have some sort of backtracking solution with time complexity 2 to the power of n. Of course, that you can reduce this time complexity using memoization, or even try to um, make the code more efficient using dynamic programming, but in the end of the day, you will have a TLE, so you're not going to be able to resolve this by using this strategy. So you need to now thinking about, okay, what am I missing here? What is the thing that I'm not seeing in this problem? Because going to this path doesn't seem to solve the problem. So if you do a few steps back, if you um, ignore the dynamic programming approach, but knowing that your problem will produce 2 to the power of n possible results, you're going to realize that this is simply a counting problem. So imagine that you have sorted your input like this one, and imagine that you are in a number 3, for instance. So now that you are in the number 3, you would like to find the maximum number that summing with 3 will result in 9, for instance. So in this case, you know that is 6. So you notice that you have a window here. So starting by 3, if you rearrange and pick or not pick the numbers inside of this window, it will always produce a valid solution. So what I try to say is that you can rearrange all the elements inside of this window and keep the 3 always inside. So if you keep 3 inside of this window always, maintain the 3 here. You can add 5, for instance, you can add 6, and you can always add all of them together. These 3 results will produce the same, it will produce this a valid solution. But why this is important? If you remove the 3, like if you decided, okay, why should I keep 3? Let's try to remove the 3, for instance, here. So in the moment that you remove the 3, it's not valid anymore, because 5 plus 5 is 10, it's bigger than 9. 6 plus 6 is bigger than 9. 5 plus 6 is bigger than 9. But if you add the 3, so if the 3 is fixed, you realize that all the solutions are valid. So this solves the problem. You realize that what you need to do is simply to calculate the number of combinations that you have inside of this window, having the first element fixed. So you're going to do something like this. 2 to the power of w minus 1, and w is the size of the window having the first element fixed. So that's how you have to do. You might ask, okay, why minus 1? Because minus 1 is, remember, we are setting the first element fixed. So by using this strategy, you can solve it. So how can we find this element to the right here? So if you order it, the numbers, you can do a binary search and find it in logarithm time. So let's solve this problem here together. So the first thing that we need to do is to declare a constant here, because the problem says that you should return the modulus of 10 to the power of 9 plus 7. So let's declare this. And you're going to need to use some sort of caching here to calculate this 2 to the power of w minus 1, because it's very expensive to calculate this all the time. So to do this, you can create a table here. So let's call this poll table and initialize our poll table. Now you can do this. So the current position of the poll table receives the previous one times 2, and we need to do the mod here. Otherwise, the number will grow very fast, and you're going to have an exception. So after this, what you can do now is simply follow our strategy. We're going to loop through all the numbers, and you're going to need to seek for a number. So I will declare a variable here, seeking number, that will be equals to nums I minus target. But I will only do this if nums I times 2 is less equal to the target. So if that's not the case, I will break. I just realized that I forgot to sort the input, so I will do this right here. So this is important because imagine that you have a number like this, 5, for instance, here. You shouldn't continue because 5 plus 5 is bigger than 9. So at this point, you should simply break because this number will not produce a valid answer. So once you have this, now you're going to need to find the number to the right. So imagine that you is in 3 here and you are looking for 6. So you can do a upper bound, which is a binary search for this value. This will return an iterator. And something very important here is that if you are looking for 6, for instance here, this method will return the first number bigger than 6, which is 7. So you need to do a minus minus it. So now you're going to calculate the window size. So let's declare the j pointer here to be it minus num.begin. Now you do the calculation. So you call this by w, which is j minus I. So usually to calculate the window size, you would have a +1 here, but remember that we have this -1, so -1 plus 1 is equal to 0. So this would be equivalent to do this. That is equal to 0. That is equal to have enough in here. So now you're going to do ans receives ans pull table table mod, and you return the answer. Let's see if this works. I forgot to declare the ans. Yeah, this works. Yes, so this is one of the solutions for this problem, and this is the most straightforward for me, but I know that not all the programming language has a method like upper bound method. In this case, you would need to code up your own binary search, or maybe use a different strategy. A different strategy than using binary search is um, to use, let's say, a two-pointer strategy here. That would be the you would have 2 pointers, one to the left and one to the right. So this is left, this is right, and you always going to ask if left plus right is less than or equal to target. If so, you would you would increase the left. If not, you would decrease the right. So if so, for instance, in this case, it is. So you would count. So you would get the window size here, and count, after count, you would move left to the right. So this is one of the ways of solving this problem as well. Let's see if I can code this up. So we would have left pointer, right pointer, and you would run the loop while left is less this equal to right. So here inside you would have, let's say, sum, that is nums left plus nums right. So if sum is bigger than target, this means that we shouldn't count here. In this situation, we should reduce the sum. So to reduce the sum, you decrement right. Otherwise, you need to count. So you would do the window size, which is right minus left. So remember, we would stay with the -1 here. So we would do ans receives ans plus pull table w mod, and we in the end we would do left plus plus because we now want to um, go to the next number. So if we execute this, hopefully it's working. Yeah, and that's other way to solve this problem. Um, I hope that this was clear. If you have any question or would like to discuss the problem with more details, let me know. Thanks for watching.